Let's review a little terminology for our buffer manager. How will it know if a page is in use? That is to say that some task or query wants to use that page right now and would like it to stay in the buffer pool. For that, we'll keep a pin count, and we'll have the pin count represent the number of tasks, the number of queries, if you will, that want to work with the page right now in memory. And then the second question, if the buffer manager is full, what page should be replaced? Well, this is going to be handled by a policy called the page replacement policy. And we're going to look at a few of those very soon. Now let's go through the life cycle of this. When a page is requested, if that page is not in the buffer pool, we're going to choose an unpinned frame. That is a frame whose pin count is 0. And that's the frame where we're going to put the new page. And we're going to replace whatever page is in there now. So if the frame is dirty, that means the page that's in that frame right now has been edited, it's been modified, since it was read from the disk. And so we're going to write that current page back to the disk. And then we can mark the frame as clean. After that step, we can read the requested page into that frame, overwriting the page that used to be there. After that, we pin the page so that we keep track of the fact that the requester is working with this page right now, and we return its address to the requester. Now, if you can predict the requests in advance, like you're doing sequential scans and you want to do read ahead, it's perfectly fine to prefetch these pages following the protocol above. So you can read several pages in at a time, and for each of them, they're going to replace a previous page following the rules that we just went through. So let's look at an example. An API request comes into this state of the buffer pool, and the request is to read page 7. As you can see, page 7 is not in the buffer pool, so we're going to have to replace one of the pages in the buffer pool. So let's say we replace page 2. You notice that page 2 was dirty, so we flushed it back to the disk. And now we mark it clean and we read page 7 into that frame. And we pin the frame before returning it back to the requester so that we keep track of the fact that the requester might want to work with this page in RAM. And then we return the pointer to that page to the requester. After the requester finishes, they must first set the dirty bit, if they've modified the page, to let the buffer manager know that the page is dirty. Second, and afterwards, they unpin the page. Now, it's helpful if they unpin the page quickly. Why? Well, if they're not using the page, someone else might use that frame in the buffer pool for another page. If you hold on to pages as pinned in the buffer pool, you basically limit the number of frames that are available for replacement. In the worst case, there are no frames in the buffer pool available for replacement, and no new tasks can get done. No new data can be brought into the buffer pool. So a well-implemented database system keeps its pins on the page very, very briefly, just to do a very basic task, and then it unpins them. And this allows the buffer pool replacement policy lots of latitude to choose which frame to replace, because lots of frames will be unpinned. After setting the dirty bit and unpinning the page, that page might get requested again. And it might get requested by more than one task. And so for this reason, we keep a pin count. So to pin a page, you actually bump that pin count by 1. And then a page is a candidate for replacement when that pin count goes back to 0. So pinning a page amounts to incrementing the pin count, and unpinning a page is decrementing the pin count. And the count itself keeps track of how many tasks currently have the page pinned. Now, concurrency and recovery may do additional IOs when they replace this page. There's this thing called a write-ahead log protocol that we'll look at later. For now, we can keep track of our simple idea that we flush pages to the database when they're dirty and when the page needs to be replaced. Now we can go back and provide some answers to the questions that we had listed previously. In terms of handling dirty pages, we asked how will the buffer manager find out if a page is dirty? And the answer is that the requester is going to mark the dirty bit on that page and tell the buffer manager that it dirtied the page. What does the buffer manager do when it has a dirty page? Well, at replacement time, it will write that page back to disk via the disk manager. Now, how is page replacement done? First, how does the buffer manager know if a page is in use? And we said the requester is going to keep the page pinned until it's done using it, and then the requester will unpin it when it's finished. And if the buffer manager is full of pages, which page should be replaced? That's handled by a page replacement policy, which we'll look at next.